All right, so today we're going to be talking about hash tables, and more precisely, two different ways of constructing and dealing with hash tables. Again, we're going to be using Paint. So we roughly talked about a few data structures this semester. The first one was lists. So lists had the advantage of being really quick when it came to adding stuff. So let's just put this here. Lists were great at adding stuff, and their complexity for it was O of 1. Oops. Okay at finding stuff. Actually, not okay. They were pretty bad at finding stuff, and that was O of n. And pretty bad at deleting stuff, which is again O of n. And those were lists. And then we had, I think it was trees. And trees were okay at adding stuff. And we're talking about perfectly balanced binary search trees. They were okay at adding stuff, and their complexity was O of log n. And they were okay at deleting stuff, O of log n. And they were okay at finding stuff, again, O of n log n. So trees are pretty balanced when it comes to these three operations. And then there were graphs. And graphs kind of had a slightly different usage. They're on a league of their own. So I'm not gonna talk about adding and finding and deleting stuff when it comes to graphs, but graphs were great when it comes to modeling a certain type of maybe real life thing. For example, modeling a country with cities and roads. You can use graphs, or modeling, is it with two L's? I think it's with one, modeling, whatever. Modeling a relations, for example, parent, child, ancestor, and so on. You can very easily use a graph to represent such relations, and the weight of the edge can represent what type of relation you have there. And you'll find such implementations actually in databases as well. So for example, Neo4j is a graph database which uses graphs in the back. It doesn't matter right now. So graphs are on a league of their own and slightly different to all the other ones. And today we're going to be talking about hash tables. And hash tables, as you'll see, are great at adding stuff. They should be O of 1. But in fact, it's O of 1-ish, not really. They're good, and actually they should be great at finding stuff as well, O of 1. And they're great at deleting stuff, O of 1. Now, you could wonder what kind of amazing data structure these hash tables are, that all their operations are actually O of 1. You'll see that there are caveats here. It's not perfect O of 1. It kind of depends on a few factors. But the gist of it is that, yeah, it is a great data structure for all of these operations if it is implemented correctly and properly. And so let's see what this hash table is all about. Okay, I'm going to leave this here. And can I move this? No, I can't. Actually, I should. I want to move this here somewhere because I don't need it, and then draw a line. Okay, so hash tables. Let's talk about that a bit. Basically, hash tables are kind of like a glorified array. let's assume that you want to save a list of text file of text in your program. So for example, you would have a list of names, so Alex and then Juana and so on and so forth. Names, and they're all text, and you want to somehow save them in a data structure such that the next one you want to add should be added in O of 1, and then finding stuff should also take O of 1, and deleting stuff should also take O of 1. Great, now that's a challenge. Okay, so what do you do? In case of a hash table, let's introduce a few terms. For once, what is a hash function? A hash function is something that takes what you want to enter, or the content of what you want to enter, and transforms it into a key. And that key is always going to be a natural number. So imagine a hash function being something like this: h of x, where x is, for example, Alex or Juana or Yana or whatever, is equal to, and actually it's going to turn into something like an n, where n is equal to a natural number, and it has to be a positive number, and you'll see why in a jiffy. Now, based on this n, we will know where inside of an array we will insert that entry. So again, these things over here, there are entries, and each entry has a specific hash value, and this value is the one returned from the hash function. For example, let's assume that we have an array, and let's draw a few of these things. And so on and so forth. It doesn't really matter. Let's assume that our hash function is nothing more than, so h of x is equal to the sum of all letters of x, all letters of x, modulo the size of our array. So let's assume that the size of our array is whatever, 7. Doesn't really matter. So this is 7. Whoa. Okay. And now let's add up all the letters of my name, Alex. So let's bring up an ASCII table. Okay. Un momento. Okay, this is what I need. Whoa. Okay. So the sum of all my letters should be something like big A, which is 65, plus L, which is 108, plus small e, which is 101, plus x, which is 120. So that would make up to be, let me just compute this. That's 394 modulo 7, which is 394 mod 7 is 2. All right, so this 2 is going to be the index at which I will insert Alex. It's going to be here. So I insert it here in my array. Is everything clear so far? Great. I'm guessing it is because no one's saying anything. Does anyone have any questions? Let me rephrase that.
We can't see your screen now.
You can't see my screen? What?
Yes, for a few minutes.
For a few minutes, really?
I mean, 1 or 2 minutes, not so much.
Okay, how about now?
It's okay now.
It's okay now. Good, great. I'm sorry. I don't know what the hell happened. All right, so I computed, I guess you saw me drawing this big thing, right?
Yes, that's right.
Okay, so I just computed the sum of all the letters from Alex, and that gave me 394, and that modulo 7 is equal to 2. That 2 here is the result of my hash function, and my hash function in this case, this thing, was just the sum of all the letters modulo the size of the array. Why do you think I need this modulo size of the array? It's not a rhetorical question you can answer. Please feel free to do so.
Not get out of bounds?
Simply put, yes, to not get out of bounds. Exactly. Now, again, this is called a hash function, and it's really important. It's actually the most important thing when it comes to a hash table, because this hash function has a few properties. First of all, it has to return a positive integer, which is at most the size of the array. So, well, actually, the size of the array -1 because we're implementing it in C, but it doesn't really matter. So that's its first property. Its second property is that it kind of has to the second property, it really does have to return the same thing if you inputted the same value. So in case I execute this with Alex again, h of x should always return the same thing. So it should be deterministic, always, okay? Third of all, it should spread my values as best as possible. Now, and this is why in Romanian it's called tabela de dispersie, so dispersion table. This dispersion property has to be high when for these functions. For example, if my function were something like h of x is equal to just the first letter of my x modulo 7, then in case I would have a lot of names which start with A, I would have a big problem. Why? Why do you think that is? Hello?
Because the hash value would be the same.
Yes, exactly. So I would have a lot of hash values which are the same. And that's really bad. That's not what I want from a hash function. A hash function should, in theory, be created such that my values are spread throughout the array. But we don't live in a perfect world, and some values will be put in, will have the same hash value when put inside my hash function, regardless of how well I construct this hash function. And that's when a collision happens. When two entries have the same hash key, then we can say that these two elements collide. That's how the terminology goes in hash tables. Now, what we do in case of a collision is the thing which we'll actually be studying today. And there are two main approaches to this. Let me just erase most of the things here. Oh, bummer. Actually, you know what? I'm just gonna start from scratch. Okay, so we have two approaches. First of all, we have chaining. That's its name, hash table collision resolution through chaining. Now, what this chaining is, and what it implies, is that whenever you have a collision, so for example, we would have an array of size, whatever this is going to end up being, probably 7 or 5 or something. So it's 1, 2, 3, 4, 5, 6, 7. Okay. Whenever you have a collision, so for example, h of x returns 3, and then h of x prime or x1 returns 3 as well, we will actually just chain them in a sort of a list, okay? So in here, on the third position of the array, so 0, 1, 2, 3, here, whoops, we will actually have a list of elements. And first we will insert x, and then its next pointer will be x1. Well, okay. So here is 3, here is 2, here is 1, here is 0. And my phone is ringing. That's not nice. No, cannot talk. Okay, there we go. Okay, did you understand this collision resolution type, the chaining? It's basically just chaining all the elements which have the same key in a linked list, or a list of any kind. You can have a doubly linked list, it doesn't really matter. Yeah. Is everything clear here? This is the simplest one.
Yes.
Okay, great. So this has the advantage, well, actually doesn't, let's not talk about advantages or disadvantages yet. Let's talk about the next one, which is a bit more complicated. And hash table collision resolution through open addressing. Actually, it's addressing. There we go. Okay, now here's another way of dealing with collisions, and I'm gonna copy this thing here. My hash function will require a probe, it's called. So h of x will not just be h of x, will be h of x and y, and my hash function will be something like h1 of x plus y, or something which involves y, I, and I'll explain what this I is. Here's an example. Let's assume that let's assume that we have already an element here, and it's whatever. So the hash function of Alex is 3 for whatever that hash function was. Doesn't really matter right now. And let's assume that we also want to insert something like Jon. And maybe the hash value of Jon is also 3. So that's when a collision occurs. Now, in case of open addressing, how we deal with this collision is that we use this probe I, which usually starts from 0, and increment it until we find an empty slot in our hash table. So let's assume that our hash function is actually this. H of name is equal to sum of all letters name times I plus a constant, whatever, it doesn't have to, it doesn't really matter which one right now, times I, and this maybe could be I square, constant plus I, and all of this should be, of course, modulo 7 in our case, but it's actually going to be modulo the size of your array, okay? Now, what happens in the case of Yon, and I hope I can find on Google some ASCII sum calculator for a name. Yeah, I did. So the sum of the letters from Yon are actually, H of Yon is actually gonna be a 73 plus 111 plus 110 times I at the power of 2 plus a constant, which let's just assume is 11 times I, and all of this modulo 7. Now assume I starts from 0, and then H of Yon is actually going to be a 294, correct me if I'm wrong, times 0 squared, which is 0, plus 11 times 0 modulo 7, okay? And this will equal to 0, because it's 0 modulo 7, and that's 0. Is it? It is. Okay. Now, that means that Yon will actually be inserted in the first thing here. So I will have Yon here. Okay, let's try inserting something else, and we'll figure out what to do in case of a collision. Let's insert George. Now, H of George is going to be all this thing above, and I'm going to simplify it a bit and give you just the result. And the sum for George is actually 601. So it's 601 times 0 squared, because I starts from 0, plus 11 times 0 modulo 7. And of course, initially, this will be 0 as well. Now, we already have someone inserted at position 0, and that's Yon. Now, what happens if we increment I? Well, in that case, and I'll just write it here as H of George and Y equals to 1. And then in that case, it's going to be 601 times 1 plus 11 modulo 7. And this is going to be 611, 612 modulo 7. 612 mod 7, that is 3. Oh, what a good coincidence. 3 is also occupied. That means I have to move forward and increment my probe, which is I, by 1 more. H of George with I equals to 2 is going to be 601 times 2 squared, which is 4, plus 11 times 2, which is 22 modulo 7. And this is going to be equal to 601 times 4, that's 2404, plus 22, which is 2426. Mod 7 is, what is 24? Come on, give me help, Google. Okay, Google doesn't help me here. One moment. It's 4, actually. So finally, I can insert this here. And George belongs here. Quite the trip. Now, let's recap this a bit. I inserted 3 elements. Actually, initially I inserted 2. I just placed Alex here. I'm not sure if it's really 3 the result. It's most likely isn't, but it doesn't matter. And then I inserted Yon, and Yon I inserted in position 0. And then George, its initial hash value was 0. Then I saw that 0 was occupied. So what I did was I incremented my probe. I incremented this thing here, the I, wherever it appears, and then reran the same hash function, but with a different I, with an incremented I. And I saw that it gave me 3 the next time around, and 3 was also occupied, so I couldn't put it in position number 3 in my hash table. So then I incremented I again. So I ended up with I being 2. And finally, I have found an empty position at which I could put George. And that's why I put it in 4. Is everything clear so far?
Sure.
Anyone else do you guys have any questions?
It's okay.
Okay. So this is, roughly speaking, open addressing. Now, there are a few issues which arise. One of the advantages of collision resolution through chaining is that your hash table will never really fill up, okay? Because, well, the worst thing that could happen is that your hash function is so bad, it's something like h of x equals 4, that all the elements you want to insert will be inserted in 4 and then create a list of n elements which contain all the values which you want to enter. But still, your hash table here, this thing, won't fill up, okay? But when you're using open addressing, like in this case, in case you want to insert more elements than there are number of slots allocated in your hash table, then it is going to be inevitable that your hash table will fill up, and you'll need to do something about it, okay? Now, a problem arises here. When do you do something about it, okay? So how many percentually, like on a percentage basis, how full should your hash table be before you try to do something about it? And this is a question I put to you. How full do you think a hash table has to be before it gets really rough in finding a proper place to put an element in? So just imagine that in case you have most elements occupied, so for example, I only have 5 left there and all others are full, so the only empty one left is 5, regardless of how well my hash function works, it will be really difficult for me to find a 5, right? Now, this is a question which I actually want you to think about. Intuitively speaking, how full do you think we should weight a hash table to be in case we're resolving collisions through open addressing for us to maybe double the size of it, right? And then move all the elements in the in the next hash table. And please think about it for the next 1 or 2 minutes because I have to remake this call. All right, now, do you guys have an answer for me? How full should we wait for a hash table to become before we do something about it?
Half full.
Half full. That's a decent answer. Anyone else? Come on. There are no right or wrong answers here, okay? So just tell me what your intuition tells you, okay? Come on, give me an answer or a few answers.
I have no idea, but let's say at around 60%.
At around 60%. Okay, we're getting there. We're getting there. It's actually a bit more than that. Of course, it depends on how well constructed your hash function is. So let's assume that you have a really good, a really strong hash function. Then the probability of a collision increases exponentially once you reach roughly 80%. So assuming that you have this really good hash function, once you reach around 80%, then the chance of a collision increases exponentially. And look at this image here, and I'm going to post it. Okay. So average cache misses per lookup. That means basically average collisions. Okay. So in case you are doing linear probing, and by the way, linear probing is synonymous with open addressing in our case, and I'm going to write that in a jiffy. You have a really low chance of a collision occurring when the load factor is between 0 and 0.75, 0.80. But when you reach a fill factor of 0.80 on average, again, it depends a lot on your hash function, then things really start to accelerate and really start to be messy. So depending on your fill factor, and the average answer and consensus is roughly 75 to 80%, you would want to maybe increase the size, sometimes just double the size of your hash table. Now, what happens when you need to double the size of your hash table? Because it's not like doubling the size of an array. And here's why. Assume that we want to double it and delete this here. So we put some more elements here. That should be enough. So we would have 7, 8, 9, 10, 11, 12, 13, and I think that's it. Yep, that should be fine. So we have 7. Now, here's the catch. If I were to tell you that when I resize my array, I would need to re-index every element, every entry, why do you think that would be?
Because we need to modify the hash function to be modulo 14.
Yes, correct. So basically, this hash function gets modified because the size is different, okay? And modulo 7 becomes modulo 14. And let's just write that there. Wow, that's maddeningly unhelpful. Oh gosh. Actually, yeah. There we go. So this becomes modulo 14. Now let's assume that we don't re-index everything, okay? That means that in case we want to find George, for example, and for finding, we would need to redo this hash function, because only by redoing the hash function would we know where exactly we should find George, okay? Now, in case we don't rehash everything and we try to find George, then here we would have something like this. H of George is going to be equal to all this modulo 14, and I'm going to be writing modulo 14 there. And there, and there. Now, the results will, of course, differ for both of these. And this stays the same because 0 modulo 14 is still 0. So, okay, we get here. H of George initially with I equal to 0 will be equal to 0. We check 0 to see whether or not we actually find George here, but we don't find it. However, we do know for a fact that that 0 position is filled by something. That means that it makes sense for us to try and increment I. Maybe by incrementing I, we will find George somewhere in our hash table. When do you think we should stop, by the way? When trying to find something in a hash table with open addressing, when do we stop? When do we know for sure that it makes no sense in incrementing this probe I any further?
If we assume that there were no elements deleted from the hash table, then we can search until we find an empty slot.
Yes, exactly. So we search until we find an empty slot. And let's go further, because we didn't find an empty slot here. And remember, we're still in the case in which we incremented the size of our backing array, but we didn't rehash everything. Now, we will end up with something like 612 modulo 14, and that gives 10. The result of that is 10. 612 modulo 7 was 3. That's why we inserted it by incrementing I again, and that gave us 4. But 612 modulo 14 is 10. And we end up looking here at 10, and we see that it's empty. And by the rule we just came up with 1 minute ago, that means we should stop, because there's no point in incrementing the probe any further, because logically speaking, it doesn't make sense. I'm sure that if it's not here, then by incrementing it any further, it's not going to be there either. Because if it would have been, I would have inserted it here, right? So here's the catch. Whenever, and this is the problem here, whenever you increment the size of your hash table, of the backing array of your hash table, you have to re-index everything. That's a costly maneuver, I know, but it doesn't have to happen all that often. Okay? It costs you a bit, but on the long run, it saves you time, because the sooner you do that, and we're talking about approaching that 80% fill factor, okay? The sooner you do that, when you hit 80% or 75 or whatever, the better. Because if you keep on trying to insert elements further on that fill factor of 80%, you'll see that more and more collisions start popping up. And actually, this is what you're going to have to find out in your homework. And this is why it's going to be interesting. Okay, but until then, let's make sure that everyone understands what we just said. Are there any questions from you? No, nothing.
I do have one question about the chaining method. In most languages, we have those predefined hash maps and hash sets.
Yes.
But what is the default size for the underlying arrays? And do they increase dynamically in case of too many elements? Or
Okay, so most languages being Java, I assume, and there are some implementations in C++, and there are some implementations in C#. And you want me to tell you the default size of?
No, I mean, not concretely the default size, but the question is whether it is increasing or not, and how, is there any way to find out when I initialize a hash map or a hash set?
You can actually, at least in Java, you can actually initialize it with a size of your choosing, okay? Which is nice in case you kind of roughly know how many elements you would have. But of course, and I think in Java, I'm sure in Java it increments automatically, it just doubles automatically when it reaches, I think, 70-something%. I'm not 100% sure, but it does happen so dynamically and behind your, behind the back. You don't know about it, but it does happen.
Okay.
And I am honestly not sure whether or not any of them use chaining resolution. I'm really not sure here. They might, but you'll have to Google this, and I have to Google this as well. I don't know, but it is a valid way of using a hash table. So there isn't a best way of dealing with things. Okay. Any other questions?
Does the chaining methods change the complexity of finding?
It kind of does, because in case you have a really bad hash function and you have a more dense distribution in just some of these buckets, and they're called buckets. Okay, so this thing is called a bucket, this is a bucket, this is a bucket, and all of them are buckets, right? So in case some buckets are fuller than others, then you would have a worse time when trying to find an element in case that element belongs to those buckets. But in case they're equally distributed, and here is when, again, a really good hash function comes into play, in case they're equally distributed, so they all contain n over, in our case, 7 elements, because we have 7 buckets, and in case we have n elements, each of them should theoretically and ideally speaking contain n over 7 buckets. In case this is the case, this happens when you're lucky, because whenever you try to find any element, the complexity will be the same, right? Am I making myself clear?
Yeah.
Good, great. But of course, it's, in case you're using chaining, the advantage is that this might actually be better than having to increment this probe a lot until you actually find your element, because you have a shitty hash function. So, there's a trade-off between them. There's no real best solution. And this is why, for your homework, I actually want you to implement both, and I'll tell you more about it once we get over the questions part. Are there any more questions? Okay, I assume that everything is clear. These were the theory notions of hash tables. And for your homework, I prepared quite a few things. Luckily, I prepared them long ago. I just reused them. One moment. There is assignment number 7, and there are so-called meta instructions for it. And I will share that to you. Okay, you can see these instructions, right? Hello?
Yep.
Right.
Good. Okay, now they roughly, there are roughly 4 types of things you can choose from, but I want you to ignore all this, okay? These were not. No, actually, you know what? Let's do it this way. You have the overachiever. This will, in case you want to overachieve at this homework, you will attempt to solve both open addressing and chaining hash table problems, and you'll get 0.5 to your final mark. Trust me, it doesn't. If you solve one of them, then the other one would be really easy to do as well. But yeah, so this is the overachiever. The team achiever is in groups of 2 doing the exact same thing. So you group up in groups of 2, and you're going to have to tell me who grouped up with who. And in case you solve both of them, then you get 0.25 to your final mark. The loner will attempt to solve only one of the 2 hash table problems, and that means that he'll get 0.1 points to the final mark if he or she succeeds. And the mandatory assignment finally is that in groups of 2, you will solve just one of these 2 hash table problems. And what I really want to eliminate are these 2 things. So take into account just these 2, because you have slightly more time than usual. So you will only be able to choose between these 2. Then here's your assignment. You have 2 projects which are already built, and you'll find them in the interesting stuff folder in our repository. And these projects look roughly like this. So you have a main function, and you will have, in each project, you'll see that you'll have files containing a lot of, and I should share this thing. There we go. I've written them in code blocks, but you can just copy the code in a CLion instance. It doesn't really matter. I don't care. I just wrote them in code blocks long ago. Now you'll see that each project, each one of these 2 projects contains a few files, a few code files, and also a lot of files like this one. For example, 100.data. This is nothing more than 100 lines of gibberish data, and these strings are actually the elements or the entries which I want you to insert in your hash tables. So they're all already generated. You have 100, you have 500 of them, you have 1,000, 5,000, 10,000, 25,000, 50,000, and finally 100,000 entries, okay? And the reading from the file is already done. So both projects have the reading already done. The only things which you have to take care of actually are these functions over here. The initialization of the hash table based on this n, which is basically going to be which file you want to use. And you will find this enum here for each file. It's not important now. And then you'll have to compute the fill factor for every time you need to check whether or not it is above the max fill factor, and you'll find this max fill factor in hashtable.h. And I put it as initially as 0.8, but you'll see that your assignment actually asks you to check how your hash function and how your hash table is working with different fill factors. And we'll get to that soon. Resize hash table, and this will be a function which is only used inside the open addressing type, and then insert element, and then hash function. This is all you'll have to do, okay? Only these things. And of course, a bit of outputting, but that's something else. Okay, so let's actually open the instructions. And I will share that. Okay. So using the skeleton app provided in this folder, interesting stuff / hash tables open addressing folder, complete the implementation of the open addressing collision resolution. Okay. And here you will have an initial hash function which you can work with, which is basically summing up all the letters of the content and adding a probe I and modulo size, and an initial size factor and max fill factor 0.60. And you will have to export how many collisions there were and how many resizes there were for all these configurations. And of course, once you've built your program and your hash function, it's going to be just about changing and tweaking those parameters and then extracting all these values. It's not going to be difficult, but you'll have to, and you'll see how these initial parameters change the number of collisions and the number of resizes you'll have to do. Now, this initial size factor, as to explain it, is gonna be how large, based on how many elements you have, you'll have to allocate for your hash table. So in case you have 100 elements and you're using that data, the initial size, with an initial size factor of 0.25, you're gonna have to allocate just 20, am I right? No, 25 elements, or an array of size 25, okay? And the max fill factor for that will be 0.6. And you will change these here. Initial HT size factor, 0.25, or in case it's gonna be more or less, you're gonna change that here. And max fill factor is gonna be changed here as well. Okay. Are things clear? I know it's a bit different than what we've done before, but trust me, it's gonna be a lot of fun. Hello? Guys, are you still here?
Yes, it's clear.
Great. Similarly done for the chaining thing. And let me just open that up. And here, in case you are dealing with the chaining thing, actually not this one. Where are you? There we go. Yeah, and you can see these are the instructions for the chaining thing. And you, of course, won't have resizes and collisions, but rather standard deviation to compute. Now, here's the deal. The initial size factor is basically how many buckets you'll have based on your data. Now, maybe you have 1,000 elements with an initial size factor of 0.1. That means you will have only 10 buckets, okay? 10 buckets in which you will put all the elements, because it's a chaining collision resolution thing, okay? And the standard deviation is basically how far apart in size are these buckets. And you'll find it's really easy to compute a standard deviation. You'll just find the formula on Google. And the input for that standard deviation function should be the sizes of those hash tables. I'm sorry, the sizes of the buckets in that hash tables, okay? Is it clear?
Yep.
Good. Now, creativity-wise, you'll have to work on two different hash functions, H2 and H3. Of course, you can reuse some of this initial hash function, H1, which I've already given you. But, you know, feel free to just, whatever, use your creativity here. And here, by the way, this chaining example should have H0 as well. And this H0 should be a really bad hash function. Think of the worst thing you can create, okay? Maybe it's just something like int hash, like really bad hash function of char of content, and I won't need an I here. And this will return random +1 modulo 2. Or random +2 modulo 2. And this should be something like 0 or 1 all the time, okay? So just use your imagination and feel free to create a really bad hash function.
It still has to work. Like
yeah, of course it
okay.
no, it has to return an integer. If it returns the same integer all the time, it's fine. It has to be really bad. That's it. Okay.
All right.
And this I is actually irrelevant here for the collision, for the chaining part. All right. Questions so far?
Is it okay if we change some parts of the skeleton project? I mean, the reading in and outputting part, so that we can read programmatically and so on.
Read programmatically? What do you mean?
So to read from all the files without having to rerun the program. I don't know how.
Oh, yes, of course. Of course. Feel free. Feel free to do that. It's just, I wrote the simplest thing possible so that it won't get in anyone's way. But yeah, if you want to do that, by all means. Okay. So, no questions?
No, it's okay.
All right, then that's about it for today. And this is homework for next time. So next week, you'll have 1 week to do this. Again, I have to restate this. You'll only be able to choose from these two. So either you do both of them alone, which is going to be nice, or you group in teams of 2 and do them together, but both. Again, both of them, both the open addressing and chaining. That's up to you, okay? Just ignore the other two which were below. All right. If there are no more questions, then we're going to end it here. Thank you for participating again, and take good care of yourselves. All right. And if there are any other questions which pop up when you're starting implementing all this, just put them in our WhatsApp chat and I'll answer, okay?
Okay.
And feel free to Google great hash functions. There are a lot of them, a lot of examples there, and you can learn from them. It's fine. Don't be afraid to do that.
Can we use SHA-256?
Sure, if you implement it yourself.
Okay.
Otherwise, you don't need such a complicated hash function.
Yeah, okay.
But oh, yeah, no, by all means, if you implemented it, then sure. All right, guys, thank you again, and do take care of yourselves. Bye-bye.
Thanks.
Bye.